Okay? All right, we'll talk a little bit about XP. I was really hoping that it would be a student, but someone else showing up at all is good. Makes me feel more. All right, so we ended off a little bit like just briefly introducing scheduling in Windows XP. So, I'd like to get into the memory management as well today. So we're mainly going to talk about scheduling and memory management, mainly because we have a lot of information from the Linux chapter regarding scheduling and memory, so that we can see the comparison between the two. This table here is showing a chart of different interrupt request levels. Now, these interrupt request levels are basically sorting the different types of interrupts that are on a system. Before, we talked about interrupts in an operating system. How do we use interrupts typically? Any of the two people here, how do we typically use interrupts? Like, what are they used for? How do they? What's that? I/O is a good example. So if we are running along in a program, an interrupt can occur. So that would do exactly what it says. It interrupts the current execution, and then we need to run some sort of handling routine to process the interrupt. Okay, and when we were talking about scheduling, we kind of said in a basic way that sometimes it's desirable to disable interrupts when we don't want the current piece of code that's running to stop, right? To have something else run in its place. XP supports something a little more advanced than that, in that you do not have to just turn off all interrupts. You can turn off levels of interrupts, so that when something's running, you may not stop for some interrupts, but other interrupts that are considered more important, you may stop for and process. So they have these different levels, and this is just a chart kind of outlining what the different interrupt levels are. The operating system or the kernel can set a particular level that it would like to respond to, start running some code, and only things that are of higher priority than the level it's set would interrupt the current running process. So just an interesting, a little bit more complex way of handling interrupts. Now, one thing to note here is because Windows XP is portable, in other words, can be run on different platforms, these interrupt levels don't directly represent levels of interrupts supported by the hardware. What these are general classes that XP can map hardware level interrupts to these classes. So for example, let's see here, like the clock level of interrupt. There might not be a specific interrupt for the clock on the hardware platform that XP happens to be running on. This isn't that important, since XP really usually only runs on Intel. But if it were to run on another platform, if a system does not have a clock, the class will still be there, but there'll be no real hardware interrupts put into it. This makes it so that XP can be written for these kind of levels that we have here. Even if the hardware doesn't support it, or the hardware has more than what's supported, you can just put more of the interrupts into an individual class. It just makes it so that it's more abstract, and we can write to these levels rather than specific hardware levels. Okay. Trap handling. This is just interrupt handling that we've seen before. The kernel needs to supply code that can run anytime an interrupt is triggered. One interesting thing is the last part here. The kernel uses spin locks that reside in global memory to achieve multi-processor mutual exclusion. Okay, and this is what we've seen before with locks and spin locks specifically for multiprocessor systems. We can't use the traditional or the more simple way of locking a processor with multiple processors. We have to make it so that one will be busy waiting for the other processor, so that we make sure that no two things are executing critical sections at the same time. So in this case, the critical sections are these interrupt handling routines. Okay. The object manager and naming manager, I'm not really going to go over. This really starts getting into some of the things like file systems, and in XP it's a little more than files. Other things can be objects, but since we're not really covering file systems, we're not going to get into that. Okay, so here we are interested with the virtual memory manager. Okay, we've seen memory and virtual memory in general, and then also we've seen a specific case with Linux. Okay, XP has its own style of memory management. Okay, VM of XP uses a page-based management scheme with a page size of 4 kilobytes. Okay, if you look back at what we did with Linux, you'll see that it also seems to prefer this page size of 4 kilobytes, as do many other operating systems. The main reason is that, for example, if you are running on the Intel architecture, a 4 kilobyte page size is desirable, okay, because the hardware itself supports memory management on the chip with 4 kilobyte page sizes. So what this means is that all of the activities that you do when you are translating addresses from a logical address to a physical address and using pages and page files and all of these mechanisms that we've talked about with both virtual memory and then just regular memory management, okay, if you use page sizes and page mechanisms that are supported by the hardware, anytime you do those translations or anytime you do those operations, you get to use specific specialized functions on the chip, okay, on the CPU. This is very desirable because us writing programs or code that run to do this page file or this page table mapping, okay, and running it with regular CPU instructions, if we're doing it, every time we access memory, we need to do this operation. So if we're using the CPU to do that, regular instructions, right, general instructions to do that, it can get very slow. Okay? But if you use specialized hardware, where you can just trigger this hardware to do this operation for you and do all the calculations and all the lookups and things like that, then it gets very fast. So now all of your memory accesses and things are running at hardware speeds as opposed to our more software speed of running individual instructions. Okay? So if Intel builds a chip that has all these mechanisms in it for you handling 4 kilobyte page sizes, if you're an operating system, it's in your best interest to write your page table mechanism, your memory management scheme, with 4 kilobyte page tables in mind. Okay? Because then you can take advantage of all that specialized hardware. Okay? So does everybody see the two kind of designers with when you're creating an operating system, when you're writing an operating system? Okay? On one hand, there's the operating system designer, or the developer of the operating system, who's going to go in and write things like schedulers and memory managers and virtual memory managers, right? All these different facilities to provide to the users of the operating system. Okay? But having an operating system is no good if you don't have a computer to run it on, right? So we go to the hardware manufacturers and we get all the pieces we need to build a computer. Okay? One of the obviously central aspects of that is the central processing unit, the CPU. Okay? So now this other place that's making hardware chips, these CPU chips, their designers are sitting there, okay, what kind of instructions do we need to put on here? What kinds of memory access do we need to put in here and things like that? And they think about, well, what will the operating system writers want to do with our chips, what will the program writers want to do with our chips, so they design their chip. So there are these two different kind of creators that are developing a fully functioning computing system. So the decisions that the chip maker makes, like 4 kilobyte page sizes on the chip, influences what the designers do. They want to use 4 kilobyte page sizes because they can take advantage of what the decisions that the chip makers made. So if you're running your operating system on another chip that uses 8 kilobyte page sizes, well, you probably want to write your operating system, your virtual memory manager, with 8 kilobyte page sizes in mind. Okay? Then you run into the problem, what if your operating system can run on 2 different chips? Right? One of them using 4 kilobyte page sizes, one of them using 8 kilobyte page sizes. Well, then you have to make a decision. How much of it do I want to be portable? How much do I want to be specialized so that I can take advantage of these features? Or is there some way to make them both kind of act the same, like instead of using 8 kilobyte, we'll use 4 kilobytes still and waste 4 kilobytes of the page size? I don't know. But does everybody see those two different forces at play? There's instructions and facilities available in the chip. There are all these services we want to provide as an operating system designer. So we have to kind of find a compromise between the two when we're writing an operating system. So that's what XP did, and that's also what Linux does. And most operating systems, they're kind of catered towards a particular chip so they can take advantage of that chip. So in this case, we're talking about Intel chips. Okay. Two-step process to allocate memory. You reserve a portion of the address space, and then you assign the space in the page file. I don't know what I mean by the 2000 file, but let's get to what the addresses look like. It uses a 2-tier page file system. Okay. In our general discussion of memory management, we said we have an address that we want to access. We go look up in the page table. Right, we look for this address and we find out what frame it's in. We take the frame number, then we can go to the memory, the actual physical memory, and find an address there, and that represents the address we're looking for. Okay, so we had one tier where we go from a logical address to a page table to a frame, right, a physical address. Okay, now. Windows XP uses a 2-tier system. Okay, in this system, we're doing what we kind of referenced this in the homework and talked about it a little bit. We page the page table. Okay, so what does that mean? Our page table. This right here is not exactly paging the page table, but the idea is breaking up page tables because we can't necessarily fit them all in memory at the same time. Okay. In this case, we're not. These page tables are not necessarily one page table broken up. These are multiple page tables for multiple processes. Okay. But what we do is we have a page directory, which we can reference to find a page table. And then we go to the page table, and then we look up the frame that a page is in. Okay, so let me explain this further. Our logical address space has usually just addresses going from 0 to 4 gigabytes, right? Well, we can't reference physical memory by using a logical address because you don't even necessarily have 4 gigabytes of memory. We need to do paging, translate it. So before I said we go from go through a page table to find a frame. Okay? What XP does is it adds another layer in here. Okay? In XP we have multiple page tables or segments or pieces of an individual page table. So what we do is instead we put in a page directory where we look up what page directory we're in, and then from the page directory we look up individual entries which don't point to frames, they point to page tables. Okay? So now these individual entries of the page directory point to different page tables. Inside the page table, we now have what we're familiar with, where each of these entries in the table maps from a page to a frame. Okay? So now, through 2 hops, from going from an address to a directory to a table to a frame. Okay? What's the benefit of this? Well, the same benefits that we see with paging in virtual memory. If I'm not using a table at the moment, or I haven't used a table in a while, it doesn't need to necessarily be in physical memory. Okay, it doesn't need to be, since we're not accessing it, we can kind of stow it away so that it's not taking up resources. Okay, so even though our directory might point to, many page tables, we can have only the working set of those page tables in memory. And we can stow the rest away. So by having this extra layer, we can kind of put all these additional tables that we're not using away. Okay, even though we need to keep track of them. Because even though a process might be dormant or anything like that, it's still a legitimate process. We may swap to it or it may become active. So when it does come active, we can go load up its page table and start using it. Just update the page directory to tell us, okay, it's active and we're using it. Okay, so you can see how this is similar to why we were doing paging in the first place, only at a higher level, right? We were using paging so that, pages that weren't in use didn't take up frames, right? If we weren't using a particular section of memory in our logical address space, those can be written to disk or thrown away or whatever so that they're not taking up physical memory. Okay, here what we're talking about is saving resources of the page tables themselves, because those, even though we've been talking about them like they're outside of memory, they have to be stored somewhere, and that ends up being memory. Okay, so you're actually using up some of your memory to manage the rest of your memory. Does that make sense? Right, the page tables, the entries and everything need to be stored somewhere, and they end up getting stored in memory. So you're actually sacrificing some of your memory so that you can manage the rest of your memory more efficiently. Here we're doing the same thing where we are using the memory used for page tables more efficiently. Okay? So this is a 2-tier system. Actually, we saw something different in Linux where Linux kind of has the option of using 2 tiers of page table. And on a 32-bit Linux, I think typically it doesn't use this second tier. And I'll show you how it does that. I'll get back to this. But looking at an address, okay, before when we talked about logical addresses, right, we said we look at the first few bits of the logical address to find out what page table entry to look up. We look up the page table entry, find the frame, go to the frame, and then use the rest of the address to find the offset within that frame. Okay? You also did a homework assignment on that when we were talking about general memory management, right? Where you looked at an actual binary address and said, okay, this first part is the page, this next part is the offset, right? Here, we just break it into 3 parts instead. Now, the first few bits are for the page directory entry, how we look up a page table to go to in the directory. And then the next bits are the page table entry, which is what we remember, of looking up a frame in a page table. Okay? And then we have a page offset, which is the offset within the frame. Okay? So if you take off this page directory entry, this part of the address works the same as we saw in the general discussion of address translation. Okay? What we've done is we've added this other layer by putting the page directory entry at the front. Okay? So actually in XP, this works out to 10 bits. This is actually should be 10 as well. It's 10 bits, and then 12 bits for the offset. So if you total all that up, you'll notice it's 32 bits. Right? So 32 bits means we have from 0 to 4 gigabytes of address space. In other words, those are how many addresses we have. But they're breaking up into these pieces. Okay? So that's what the physical addresses look like. It's slightly different from what we talked about in the general sense of memory management, but you can see how it relates. There's just an additional layer to it. Okay? In Linux, we had a similar type of addressing scheme. The difference is that Linux would let you vary, depending on what platform it's running on, it could vary the size, the number of bits used in these. So if you set one of them to 0, you get back to that single layer scheme that we saw before. So that's what it does on 32-bit machines. But if you go to a larger machine like a 64-bit machine, it can start using these bits here to make the addresses different. Okay. But this is how Windows XP does it. Okay. So again, this is used to alleviate some of the burden of managing the page table entries, or the page tables themselves, okay, on the memory. Okay, so each process is a page directory that contains 1,024 page directory entries, so that's our 10 bits, right? Each one has a page table which has 1,024 entries, which is, again, 10 bits. And then each one of those has 4 kilobytes per frame, per page or per frame. Okay, so that's how we get 12 bits for the rest of the address. That's 4 kilobytes. Okay, so that's the breakdown of the address. And then we have this part here, which is interesting. The page can be in one of 6 states: valid, zeroed, free standby, modified, and bad. Okay, so we can kind of guess what some of these flags mean. Like, for example, valid and invalid, right? Like if the flag of valid is set. We saw the use of this when we were talking about virtual memory. The idea that if I go to a page table entry, right, and it's not seen as valid, that means that we might need to go to disk to load it, right? In other words, we try to go to a physical memory address, but there's no frame available for it, right? So that means we have to go through our mechanism of going and finding it on disk, freeing up a frame, and then putting this page from disk into the frame. Okay, we see other things like zeroed, modified is interesting, right? We saw modified in the sense of when you are looking for a frame. If you're looking for a frame to put a page into, chances are you'll have to kick a page out of that frame, right? Whoever's already in the frame, we need to kick them out so that we can have a free spot to load our new page that we're trying to load. Well, there are many types of pages that are in there that if they're not modified, you can actually just kick them out of the frame and not write them back to disk, right? Let's say it's program information. So let's say this is a read. I mean, this is a program code page. Okay? Where do we get program code to load into memory? Like when you want to run a program, you need to put the code into memory so that you can start executing the instructions. Where do we get that? Where do we get that code? where do we find that code? Where do we initially get it to put it into memory? Where else do we store things besides memory? Disk, right? So on disk, program code is the programs that we run, right? Like if you want to run Microsoft Word, you run a Microsoft Word executable. That's code, right? That executable is code. Well, if our code is sitting on disk, right, we have a bunch of pages of code sitting on disk in a file, right, in the program file. Well, if we're kicking this one out of the frame, this page out of the frame, we don't need to store that anywhere on disk because it's already found on disk, right? So we can kick it out, and if we ever need to load it again, we'll just go back to where we loaded it from the first time and put it in. Well, that's different for data, right? If you're running a calculation and storing variables with parts of your calculation, those variables are in memory. They're in a page of memory somewhere. Well, if we come along and say, well, I want to use this frame, I need to kick you out, I need to kick this page out, right? We can't just erase it. We can't just erase that page and start using the frame. Why? Because all of our values in there we need to keep. So what we need to do is write this to disk, and then we can clear it out and load something new there. Okay? Well, we need to keep track if the page is modified so that we can know whether to write it back to disk or not. So we see some flags like modified. And bad just means that that page is wrong in some way and that we need to, the operating system can handle that difference. Yeah.
Suppose it's a user program.
Yeah, this is all with user. This is mainly referring to user.
Written program, and when you done, it's not anywhere. But at that point, if the data is there, and it's to be removed from there and sent to the disk. So in that case, what happens? If I don't run the program anymore, but the data in the disk, what it happens to that?
No. It's not writing it to just any file. It's writing it to swap disk. I mean to swap, which is on disk. It's just a big file on disk that represents memory that's managed by the operating system. So if you terminate your program, all of your pages that are written to disk in the swap file, it can clear those out too. These aren't files like just sitting in your directory or whatever in your regular file system. These are going to be these are pages that are inside the swap file. Okay. All right. The process manager. This is part of the executive. If you don't remember, the executive is in the breakdown of the pieces that are in the privilege space. The executive are a bunch of different services that are run in privilege mode that interact with the kernel and the hardware and things directly because they're below this dotted line here. So the executive does a lot of additional services that are more complex than what the kernel provides. Okay, so the executive has a process manager here, okay? And it does things like creating, deleting threads, okay? And then it creates, it is in charge of these relationships between processes. We've seen these relationships between processes when we talk about things like fork and thread, right? When we do threading, two different threads are related to each other and that they share the same memory space and whatnot, okay? And then when we do things like fork, right, two different processes are related, and that one is the parent process, another is the child process. So this is kind of, the process manager is in charge of the more fundamental creating and deleting, and then it also lets environmental subsystems, these are little subsystems that do things like run the DOS programs, the Windows programs, the OS2 programs that we saw in that hierarchy as well, can handle the process relationships inside that subsystem. Okay. I'm not going to go into too much detail on the local procedure call facility. Local procedure call facility, though, is um, a subsystem which allows for those different types of communication we saw when we were talking about inter-process communication, or we saw different styles of communication where we do things like shared memory. We had message passing, right, using the mailboxes where we leave a message with the kernel and then another process can come and get that message from the kernel. This is of that style, that message passing style of I leave a message in the mailbox in the kernel, somebody else can come and pick it up. Okay? So this whole mechanism is for that, and this is handled by a piece within the executive. Okay, but we're not going to go into too much detail on that. Okay? Another piece of the executive is an I/O manager. Okay? If you look at the list of responsibilities that it has, file systems, cache management, device drivers, network drivers, okay? These are all of these different things like the queues that we saw when we do things like ask information from disk, right? If you're a scheduler, right, you schedule time on the CPU. Whenever one of your processes goes and says, oh, I want to read some disk information. Well, now we take that process, right, and then it becomes enqueued upon the disk handling scheduler, right? The disk handling scheduler decides, okay, which process gets to go access the disk next, and all of those things, very similar to a scheduler for the CPU. Okay? Then once it gets done, we can move it back into the CPU scheduling, and it can start running its instructions again. So this is this subsystem handles all the different management issues surrounding use of these different I/O devices like disk and whatnot. Okay. Cache manager. Yeah, so I mean, this synchronous, asynchronous operations, this is what we're talking about. The asynchronous operations are when you can request something from disk and then just wait for an interrupt to come back and then eventually handle it. Okay? So, that's generally what the I/O manager does. This is just get into a little bit of they get into a little bit here of like using a cache manager. This is we didn't really talk a lot about I/O caching, except in the general sense of talking about caching. And the idea of caching is you use this faster medium to help speed up a slower medium. Well, cached I/O is the idea of using whenever you access the file system. Sometimes you actually go to disk. Sometimes you can shortcut and utilize information in the cache rather than going to disk. So the cache being in memory. Okay. So if you're reading some data from a file over and over, well, the first time you read that data, you'll go to the disk, pull it off disk, but then you'll kind of keep a cached copy in memory so that as you read more and more, you can start going to memory instead of disk, or something faster than your disk. Okay, security reference monitor. This is a part of the executive that handles all the permissions and accesses on different objects within the operating system. So this will handle a lot of the functionality that we talked about where we had the domains, right? Where we have the domains and different objects and permissions. We go through this security reference monitor to make sure that all of these, to validate all these different accesses to objects to make sure that they're allowed. Plug and play manager. This is a convenience layer for utilizing hardware where you add new hardware, and then the plug and play manager is responsible for kind of determining what kind of drivers to load and whatnot, and get the hardware ready to use by the operating system. Okay. The environmental subsystems, these are outside the executive, okay, and these are just generally what we saw for running different types of programs, right? We have Unix-style programs, DOS, Windows-style programs, OS2. These are all processes that can run individual programs. So if I have a DOS-style program, this environmental subsystem runs the program. If I have a Windows-style program, this environmental subsystem runs that program. If I have a Unix-style program, this one will run that program. Okay, and we talked a little bit about the benefits of having that in user space as opposed to privileged space. We talked a little bit about that in the sense of if one of them goes wrong, it doesn't corrupt the rest of the operating system. It doesn't bring the system down. You can add new subsystems if you want to run different style programs and whatnot. Okay, so those are the different pieces to the executive and then those environmental subsystems. Okay, file system we're not going to get into. And networking we're not going to get into. So we can get to okay. Programmer interface to Windows. We have different. This programmer interface are different calls that we can make in software. Okay, as a when writing like user level programs. Okay, we can call some of these different calls to interact to communicate with the kernel. So we can do things like we have this concept of creating handles on kernel objects. So what does that mean? You can request from the kernel, can you create a particular type of object for me? This might be a window, file, a lock, all these different things that the kernel is responsible for. So you can ask the kernel, hey, can you create a handle of type X for me? Okay, or create an object of type X for me. And then the kernel will say, okay, I'll create this object for you. It looks like you're allowed to create this object. I'll create it. But then it gives you a handle, which is kind of like a pointer to the object you've created. So now you can interact with that handle, and it will interact with the kernel object. Because we can't let them run the kernel code directly, right? We need to have that mediated by the kernel. So we let them interact with the handle. The kernel can take those interactions with the handle and say, okay, I'll make the object do different things because based on those requests. Okay, so handles are like pointers to objects. Okay, the main thing is that these pointers are pointing to kernel objects that the kernel is in charge of. Okay, 3 ways to share objects between processes. A child process inherits a handle to the object. So if I fork to a child process, that typically means we get a copy of all of the things that the parent had. So any handles that it has, we can also have access to. Okay. One process gives the object a name when it's created, and the second process opens that name. So that's kind of like our named pipe types of ideas, where we have we create a handle to an object. We tell another process the name. That other process can access by that name, given appropriate permissions by the kernel. Okay. And then we have the idea of duplicating a handle. This is really just like copying a pointer. You have a handle that the kernel gave you. You can copy it and then give it to another process. Okay, this is really just to introduce you to the concept of a handle in Windows. It's something that's typically used in any Windows programming, whether you're doing like your windows that you actually see on the screen. Each of those graphical objects have a handle that you interact with to do Windows programming. Disks and things like that. Yeah.
Like when you do it in VB, little graphics,
Yeah.
same thing?
Well, through the layers of indirection of VB. Eventually, somewhere, something created
Not direct.
a handle. What?
It's not direct.
These days, I mean, VB is pretty compiled, what I'm saying is that you typically don't see the handle objects in VB.
Like in C++?
In C++ you
When
do.
you create a window,
In C you do.
so you can say like, you can actually call on
A handle is actually just a regular data structure. Like in C, you can actually,
really
it's,
create a handle.
yeah. I mean, they all return the same handle from the operating system. In C, you see it. In VB, you just see the concept of a window, which is encapsulating all that stuff. But they all use the same handles eventually. It's just a matter of how you interact with it. So you can have a very pretty object that's dressing it up so that you can call methods on it and it manipulates the window. Or you can be in C where it's just a data structure and then you call functions on that data structure and manipulate it. But yeah. And that's typically where you see it with programming Windows is the actual window handles and things like that. But almost anything that the kernel's in charge of will be interacted with through handles. Okay. Also interesting is the idea that even processes and threads are created and manipulated the same way. So they have handles to these threads and processes. Okay. Process management, again, this kind of goes more with the scheduling that we saw before. 4 different priorities. We have idle, normal, high, and real time. Okay, and we saw before that this real time is soft real time. Okay, very much like your typical operating system's real time is not hard real time where you can guarantee how long something will take or how long it will take to respond to something. This is, I'm going to attempt to respond within a particular time limit. Okay, but we have these different priorities. Okay. One of the biggest concentrations of the scheduler in XP is interactive scheduling. Okay, is making sure that performance is very high with interactive processes. Okay, so these interactive processes are when we're doing a lot of I/O, when we're waiting for the user, interacting with the keyboard, mouse, graphical user interface, all of those pieces. Okay, so we will prioritize these very high. Okay, and we will. When we prioritize them as high, what does that typically mean in a scheduler? We're going to have shorter time slices, but we'll service them often, okay? As opposed to our other priorities where we're going to give longer time slices, but not do them as often. Okay? And then we even have a priority called idle priority, which is when the CPU is not being used, we'll start running these priorities as much as we can, okay? So XP distinguishes between foreground and background processes. Okay, this is a concept of foreground and background in the sense of the graphical user interface, and then also the fact that they are interacting with the user. There's a concept that usually the top level application is the one that you're interacting with. Okay, and it distinguishes between these different applications mainly because you can set XP to make sure that the foreground application gets the highest priority. Because even though another program might be on screen and be interactive, if it's not the foreground one, it's not interacting with your input-output, right? Some of its output might be interacting with you, but it's not getting your input because it's not selected. Okay, so prioritizing those differently, where you prioritize the foreground one higher. Again, the higher we get, the more often we service that, and probably the smaller the time slice, so that we get very, very responsive foreground apps that are getting serviced often, and these background ones, if they need, they can wait, right? But when we do get to them, we'll give them a little bit more time. Yeah.
Well, I was saying like there should an application for focus and background, like you'll be giving input to them, like data loggers and stuff.
Oh, like disk input? Like I/O from disk? XP distinguishes between disk and... It sees keyboard and mouse as a very different set of inputs, so they'll prioritize a particular way. But the thing is and at least for the applications that it does, that actually makes sense, because disk I/O, although it is input-output, what makes it very different from keyboard and mouse type of input-output? Fast in the sense that faster than a person, right? Than the person, yeah, than the clicking and typing on a keyboard. And it's also you're not waiting for a decision from a disk. You're just waiting for the actual I/O. So it is more like a CPU. I mean, it's an area between kind of, we have CPU bound where we're just trying to use the CPU. We have a wide array of different types of I/O, right? At the slowest end, it's the person, right? So that's mouse and keyboard. And then in between that, there are things like network and disk and stuff where it's more still all, there's no person involved in it, but it is slower than executing on the CPU. So even though these other processes that aren't selected might be doing I/O, they're not doing the type of I/O that's considered interactive I/O by XP. As we run these processes, their priorities will get shifted around based on, we saw this a little bit before talking about scheduling. We briefly mentioned it with XP and then also saw it with Solaris. The idea that the reason for a process leaving the running state can give the operating system scheduler clues as to how to adjust its priority, right? So if you're a process running and the reason that you stop running is because I have preempted you, right, and taken you off the CPU, okay? That's one scenario. Another scenario might be you're running along and then you yield the CPU so that you can go into a waiting state, right? That's another way that you might get off the CPU. Okay? Which of those indicates that you're an interactive process? Which of those two scenarios? Does everybody understand the two scenarios?
One is preempted and another is like.
One is preempted, it was running, it stopped, taken off the CPU so something else can run. The other is the process is running, it yields the CPU and goes into a waiting state. Is what? Is an interactive process of some sort, right? You yielding means, or the process yielding means that I am going to wait for something like I/O. Whether it's, right now we haven't determined whether it's disk or it's, keyboard or mouse, but we'd know why it's yielding if we were the operating system. Okay? If you are getting preempted, that indicates that you are probably leaning more towards CPU bound. Why? Because if I were to give you more CPU, you would have kept using it. I had to stop you. Okay? So these different ways that we get a process off the CPU, these are indicators as to what kind of process you are. So when you do a lot of yielding of the CPU to the operating system and saying, I'm going to wait for keyboard, I'm going to wait for disk, I'm going to wait for mouse, right? If you keep doing that, the operating system is going to say, oh, you're probably interactive. I'm going to start moving you towards the interactive queues, right? So that you can get these smaller time quanta, but larger, but more often interaction. If I keep having to preempt you, I'm going to move you towards these CPU-bound processes where I'm going to give you longer CPU bursts, but not service quite as often. Okay, so that's how we dynamically adjust these priorities as they're running. Okay, so it uses these heuristics to determine what kind of process are you. What would be a good queue to put you in, because we don't want every single process to have to we can't depend on programmers to tell us what kind of process they are. Why? Because they'd always say they're the highest priority process so that they keep getting time slices. Okay? Synchronization in a process, access to shared objects by threads, and then also synchronization objects like semaphores and mutexes. Okay? So we've seen these types of synchronization objects in our general synchronization. The process management of XP is responsible for managing those locks and things so that user-level processes can coordinate themselves and synchronize. Okay? Threads can synchronize using these two calls that we see in this bullet. Okay? These are just kind of like, we saw them in a more general sense of the calls that we did, like locking and unlocking of these semaphores. Okay, these are specific Windows calls that we use for that. Okay, where you'll wait at a lock, and then eventually something will unlock it and notify you that it's unlocked so that you can continue through. You can also tag inside the Win32 API. There are ways to tag parts of your code as critical section. And what that will do is ensure that only one critical section is running at a time. In other words, it's like putting a lock at the beginning and end of a section of code. They have calls within the API that can facilitate doing that in your code. Okay. What else? We've seen a little bit already about inter-process communication of using kernel objects to pass messages between each other. Memory management. These are just two specific calls for allocating memory inside Windows. Not much to say there. This is just the actual call that we'd use to do all of these kind of theoretical things that we were talking about, getting memory, getting ourselves pages of memory, and then in the background, the operating system will do all the manipulation of the page files and frames to facilitate that. Okay? It would allocate us the memory. When we actually start writing to the memory, it'll find a free frame, zero it out for us, and let us start using it. And then if it ever needs to be swapped out, it'll handle writing it to the swap file and whatnot. Okay? These are just specific calls that if you were writing a program and you needed those, and you needed more memory to allocate dynamic memory, this is how you do it. You'd see it in Unix as things like malloc. Okay, that would be the equivalent in Unix and Linux types of operating systems to these calls. Okay. This is a heap. That's about it. Okay. The main things, a lot of that was description of all these different pieces of Windows XP. The main ones I'm interested in are the scheduler and the memory manager. So make sure you look through like these types of concepts in the process management. We have the different priorities. The operating system wants to detect whether you're I/O bound or CPU bound so that it can start moving you into the appropriate priority. We have here. Memory management, okay? The format of the addresses, the idea that we have a page directory which points to page tables. Those page tables point to individual pages. We have different priority levels. These two slides here on kernel scheduling, coupled with those later slides on process management, okay, that kind of gives you the overall idea of how Windows XP schedules. Okay, we have this concept of these different priority levels, right? And then we have the scheduler and the process manager, which are trying to sort out all of these different threads into their priorities based on whether they're doing I/O, whether they're doing CPU. So we have this multi-queue system which dynamically moves processes between the queues to favor I/O bound for high priority and then CPU bound for lower priority. Okay, and then we also have a separate range of soft real-time threads so that we can do very high priority scheduling. That's about it. But those two are the main interesting things, the scheduling pieces and then the memory management pieces. Okay? And I'd especially look at these two chapters together, the Linux chapter and then the XP chapter, so you can kind of see the differences between the two. Okay? Linux is very straightforward. It's scheduling in the sense of it it still has the multiple queues, but then it does this system. The interesting part is the system of moving them into another queue, and then once you're empty, you flip back and start servicing them again. So these two differences, keep an eye on those. And then the memory management, they both use generally the same idea, but each has a few different details. Okay. One of the main things is that XP does definitely use this page directory idea, whereas Linux it's kind of optional when it's doing memory management. Okay. The rest of this stuff is in this chapter is really just so you'll have a general idea of what's involved with an actual operating system and what kinds of pieces are needed to implement all these different kind of theoretical concepts that we've been going over. Okay, so all right, that is it for the book material. Okay, like I said, we are going to go over on the presentation days. We are going to go over a bit of a review as to what to study for the final. I'll say what I said before, which is on the final, we are going to continue into basically just cover the new material since the midterm. It's not cumulative. The main things I'm interested in are memory management and are mainly this memory management and virtual memory. Those are the kind of big concepts we went over. And then a little bit on protection security and a little bit on Linux and Windows XP. But both of these go together. Protection security is kind of, think of those as equivalent to the memory. Both of those together are kind of equivalent to the memory management chapter. Both of them are equivalent to the virtual memory chapter. Okay. Same with the Windows XP and Linux. Those are two can be seen as kind of together. So the main focuses are the two big concepts are the memory management and virtual memory. Okay. And then, oh, actually, did we do deadlocks on the test?
Yeah.
We did do deadlocks on the test. Okay. So yeah, these two are the main ones. And use the homeworks that you've been given as the guide to what kind of things I'm interested in as far as topics for the test. Okay, so make sure you get to me your homework for today. I think I've seen some of you have already turned it in. The next thing is also that your slides are due Tuesday. Some of you will present on Tuesday, and I'm going to pick on Tuesday. Okay, I will send out an assignment which has so that you can submit your slides. Okay, just a handful of slides. It's a short presentation, just introducing us and telling us what you learned from your project. The final report is going to be due on the day of the final. Tuesday the 12th. I looked up the time before. It's like 10 o'clock? Okay. So it's Tuesday at 10. I'll be in I'm in the office today. If I need to be I'll probably be in the office Monday as well, since the first slides in your presentation are due on Tuesday. So I'll be in the office on Monday as well. Give me a call. My number's on the page. I think it's on the syllabus, but give me a call or send me an email so that I can make sure that I'm in there at the time that you want on Monday if you want to come by. Huh? Yeah, it's on WebCT. But so I'll be available on Monday, and then also email. You can email me and WebCT me this weekend if you need stuff, or Friday. But I'll also be in the office today, so if you want to come by. That's it.